Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will start on chapter 5 about improper integrals. This chapter includes two sections. First section about orbital rules, which is when we have 0 over 0 or infinity over infinity, and how to evaluate the improper integrals. We have two types of the improper integral that we will discuss through this chapter. Okay, first, what is the orbital rule? When we calculate the limit of the ratio of the two functions f of x over g of x, okay, we usually substitute when x goes to a, we usually substitute the value of a on the function f of x and the value of a on the function g of x, and the result will be the answer of the limit. But sometimes we have 0 over 0 or infinity over infinity. In this case, we have to apply what we call orbital rules. Orbital rules state that if the limit when x goes to a to f of x over g of x is equal to the limit of the derivative of f over the derivative of g. But before we going for orbital rule, let us say how we calculate the limit. To calculate the limit, we substitute the value of a on the function f of x and the value of a in the function g of x. For example, the limit when x goes to 3 for x squared plus 1 over x plus 2, we need to replace x by 3. So 3 squared plus 1, which is 9 plus 1 is 10. 3 plus 2 is 5. So we will substitute x by 3. We will replace x by 3. So here 3 squared plus 1, which is 9 plus 1, 10. 3 plus 2 is 5. 10 over 5 is equal to 2. So the limit is equal to 2. Okay, so what will happen if when I substitute, I have 0 over 0 or infinity over infinity? Then in this case, I will apply the orbital rules. The orbital rules indicate that if the result of when you substitute is 0 over 0 or infinity over infinity, you have to evaluate the derivative for the function f and the derivative for the function g. So the limit for f of x over g of x will be equal to the limit for the derivative of x with respect to x over the derivative of g with respect to x. Yes, it's equal to L. So we need to evaluate the derivative for the function of x and the derivative for function g of x. In the case that the limit goes to infinity or minus infinity, so the limit f of x over g of x also will go for infinity or minus infinity. In this case, we said that this is a divergent limit. Okay, here we have an example. We need to calculate the limit of sine x over x by orbital rules. The limit when x goes to 0 for sine x over x. Here, if I make a direct substitution, sine 0 over 0 will substitute x by 0. So sine 0 is 0 over 0, so I have 0 over 0. This is undefined. So how I calculate the limit? I will take the derivative for sine x and the derivative of x. I will apply orbital rules. We will take the derivative for sine and the derivative for x. So the limit for sine x over x will equal to the limit. The derivative of sine is cosine. The derivative of x here, the derivative of x is 1. So cosine 0 over 1. Cosine 0 is 1 over 1, which is equal to 1. So the limit of sine x over x is equal to 1. First substitution give you 0 over 0. So you need to substitute, you need to calculate the derivative for sine x and the derivative for x. So cosine x over 1, now substitute again. So cosine 0 is 1 and over 1 is 1. Okay, for this example, I need to calculate the limit for 2 natural logarithm of x over x minus 1. First, I will direct substitute x by 1. So 2 ln 1 over 1 minus 1. 2 ln 1 over 1 minus 1. So the natural logarithm of 1 or ln 1, this value is equal to 0. 1 minus 1 also equal to 0. So 0 over 0, which is undefined. I have to go for Hopital rules. Hopital rules, that means I will differentiate 2 ln x and x minus 1. Now, the differentiation of 2 logarithm x is equal to 2. 2 is a constant. The derivative of ln x is 1 over x. 1 over x. Now, the derivative of the function x minus 1, the derivative of x is equal to 1. Is equal to 1. Now, substitute by 1. 1 over 1 is 1, multiplied by 2 is 2, which is 2. So, the limit equal 2. The limit equal 2. If I couldn't calculate the limit directly, take the derivative for the top and below. Take the derivative for the function here, 2 ln x, and the function below, which is x minus 1. Okay. Now I need to find the limit when x goes to 0 for exponential x minus 1 over x. Exponential x minus 1 over x. Now I will go for direct substitution. If you go for direct substitution, e of 0 is 1. E of 0 is 1. 1 minus 1. Here, if we need to go for direct substitution, it would be 1 minus 1 over 0, which is 0 over 0. 0 over 0 is undefined, so I will apply Hopital rules. Hopital rules, which means that I will take the derivative of the function e of x minus 1, and I will take the derivative of the function x. The derivative of the top here, exponential x minus 1, the derivative of exponential same, minus 1, the derivative of constant is 0, over the derivative of x is 1. The derivative of x is 1. Now substitute by 0, exponential 0, which is 1. So the limit is 1. So similar for this example, direct substitution, cosine 0 is 1. 1 minus cosine 0, 1 minus 1 is 0 over 0. So the direct substitution give you 0 over 0. So you have to apply Hopital rules. You have to apply Hopital rules. So Hopital rules, that means I will differentiate 1 minus cosine x and also x. The derivative of 1 minus cos x, the derivative of cosine is minus sine. The derivative of cosine is minus sine multiplied by minus, so sine x. The derivative of x is 1. So the limit for sine x over 1, which is equal to 0, which is equal to sine 0, which is 0. So the limit is equal to 0. Now, same if I apply Hopital rule when I get 0 over 0. Same if I get infinity over infinity or minus infinity over minus infinity. Same rule can be applied. Same rule can be applied. If your direct substitution give you infinity over infinity, then take the derivative for the numerator, take the derivative of below here, denominator, then the limit will be equal to the limit for the main functions. So I will apply here for this example, limit when x goes to infinity, x squared over exponential x. Now direct substitution give you infinity over infinity. When substitute x by infinity, infinity square, which is infinity, exponential infinity, which is infinity. So I have infinity over infinity. So it is undefined. I have to apply Hopital rules. So the derivative of x squared is 2x. The derivative of exponential x is itself same, exponential x. The derivative of x squared is 2x. The derivative of exponential x is exponential x. So if I substitute, still infinity over infinity. 2 multiplied by infinity is infinity. Exponential infinity, still I have infinity over infinity. So I will apply Hopital rules again. So I will differentiate the numerator and the denominator. The derivative of 2x is 2. The derivative of exponential x is exponential x. Now I have, when I direct substitute, here I have 2 exponential infinity is infinity. 2 over infinity is 0. Any number over infinity is 0. Any number over infinity is 0. Is almost 0. So 2 over infinity is 0. So the limit equal to 0. Limit equal to 0. This is another example. Direct substitution will give you infinity over infinity. So you have to apply Hopital rules. You have to apply Hopital rules. So when limit x goes to infinity, then x square over x. This one infinity over infinity. So by applying Hopital rules, you need to take the derivative for the top here, numerator, over the derivative of x. The derivative of ln x square is equal to 2 ln x, 2 as a power function, 2 ln x multiplied by the derivative of ln x, which is 1 over x, which is 1 over x. And the derivative of x here is 1. The derivative of x here is 1. So this one give me limit when x goes to infinity, 2 logarithm x over x. This one, this x will become below here. This x will become below. So 1 over x here, x will become below. This x will become below. So you will have 2 logarithm x over x. Substitute by infinity, you still have infinity over infinity. You need to apply Hopital rules again. You need to apply Hopital rules again. So here we will have, when apply Hopital rules again, I will differentiate 2 logarithm x and I will differentiate x. 2 logarithm x, which is 2. Derivative of logarithm x is 1 over x. The derivative of x here is 1. Is 1. Substitute again. So 1 over infinity is 0. Any number over infinity is 0. 0 over 1, which is 0. So the limit equal to 0. The limit equal to 0. Okay, now here the improper integral. The improper integral. Now the improper integral, I have the function f of x from a to b. Okay, what we call this integral is improper integral when one of the boundary goes to infinity. When one of the boundary goes to infinity. A, for example, a is infinity or b is infinity. Or sometimes both. Sometimes both. Then we call this integral is improper integral. This integral is improper integral. Or sometimes we have a point between a and b, or maybe a and b, the function f of x is undefined at this point. Okay, undefined at this point. In this case also we call this integral an improper integral. But in this case we have two types. We have two types of improper integrals. When I have a problem on one boundary, or I have a problem on the two boundaries, or in the number in between, because sometimes I have to separate the integral into two integrals. Let us go for example to clarify this. Now this is the first case, type 1, improper integral type 1, when I have the above boundary goes to infinity. The above boundary goes to infinity. Now how I can evaluate this integral? I will take infinity here, any number t, and I will replace it by any variable t, and then I will evaluate this integral. After I evaluate the integral from a to t, I will take the limit when t goes to infinity, because here the improper integral is infinity. So I will replace the infinity by the variable t, and I will evaluate the integral. Then I will, after I evaluate the integral, I will take the result and take the limit for the result when t goes to infinity. If the problem on the lower boundary is minus infinity, same, you will replace the minus infinity by the number or variable t, and then you evaluate the integral. Then your result, take the limit for the result of integration when t goes to minus infinity, If the problems on the two boundaries, the lower and upper, both are going to infinity, then you need to separate the integral into two integrals. First one from minus infinity to c, and second one from c to infinity, where c is any number. Usually we take c equal to 0. But c can be any number. This is, for example, the integration from 0 to infinity exponential minus 2x dx. So I will take the limit. Here the problem on the upper boundary. Our upper boundary is infinity. So I will take the limit when t goes to infinity. The integration from 0 to t, I will replace the infinity by t, and I will take the limit for the result when t goes to infinity for exponential minus 2x dx. Now I need to evaluate this integral. The integration of exponential function is same, exponential minus 2x. I will divide by minus 2 because x is multiplied by minus 2. So the integration is exponential minus 2x over minus 2. The boundary of integration from 0 to t. So I will substitute by t. So exponential minus 2t over minus 2 minus substitution of 0. So exponential 0 over minus 2. And this result, we have to take the limit when t goes to infinity. Now it is equal to the limit when t goes to infinity, exponential minus 2t over minus 2. Here minus become positive. Exponential 0 here is 1. Exponential 0 is 1 over 2. So the limit here, when substitute by infinity, we have exponential minus infinity. But this one is minus 2t, so we can bring it below. So 1 over minus 2 exponential 2t. Here the minus 2t will take it below exponential 2t. Plus the limit of 1 over 2. The limit of the constant, same constant, 1 over 2. Now here substitute t by infinity. So this one become infinity. 1 over infinity. Any number for infinity is equal to 0. So 0 plus 1 over 2, which is 1 over 2. The limit is a number. Then we call this integral is converge, because after we evaluate the integral and take the limit, if the limit equal to any number, we say that this integral is converge. If the limit goes to infinity, then the integral is diverge. Okay, here this example, the problem here in the infinity here. So this is an improper integral with a problem on the upper boundary. Upper boundary infinity will be replaced by any variable t, and the limit when t goes to infinity, x exponential minus x dx. So I will evaluate this integral. I will substitute from 0 to t, and I will take the limit. Okay, first, how I can evaluate this integral? I will use integration by parts technique. I have a multiplication of two functions, one function for derivative, one function for integration. So for derivative, u is equal to x. For integration, dv exponential minus x dx. Take the derivative for this part, then du is equal to dx. Take the integration for this part, then v is equal to minus exponential minus x. Minus the integration of exponential same divided by minus 1, which is minus exponential minus x. Now the limit when t goes to infinity for this integration is equal to the limit when t goes to infinity. The result for this integration, the result is uv. I will apply the rule uv, which is x minus exponential minus x, uv, minus v du, minus the integration v du, the integration v du, minus minus here become positive, integration v du, exponential minus x dx, exponential minus x dx. I will substitute from 0 to t, the boundary of integration from 0 to t. Now substitute t first. Here the integration, the evaluation for this integration, exponential minus x is minus exponential minus x. So now I evaluated the integral. I will substitute from 0 to t. First apply t, substitute t. So I have minus t exponential minus t minus exponential minus t. So I substitute t first. Now minus substitution of 0. Minus substitution of 0. When you substitute 0, this term goes to 0. When you substitute 0 here, exponential 0, which is 1. So minus minus exponential 0, which is plus 1. Plus 1. Now you have this limit. Okay, so this is 0 and 1 are constant. Now the limit for this term, I will distribute the limit here. So I will take the limit for this term and the limit for this term. So the limit for the first term, minus t exponential minus t, is equal to minus t over exponential minus t. Here I will bring it below, so it's become exponential t, minus the limit when t goes to infinity for this term, which is minus 1 exponential minus t, which is exponential t, Here is 1. Here is 1. Okay. Now plus 0 plus 1, plus 0 plus 1. Now go for the first term, substitute by infinity. So I will have infinity over infinity. So here I have to apply Hopital rules. Here I have to apply Hopital rules because I have infinity over infinity. The derivative of minus t is minus 1. The derivative of exponential t is exponential t. Now 1 over exponential t, direct substitution, exponential in infinity, which is infinity. 1 over infinity is 0. 1 over infinity is 0. So 0, and we have here from 0 plus 1. Now this term I will direct substitute. I already differentiate minus t, which minus 1, exponential t is same, exponential t. Now direct substitution, minus 1 over infinity, which is 0 also, which is 0. Any number over infinity is 0. So I have 0 plus 1, which is equal to 1. Since the limit is equal to the number, then the integration is converge. Okay, another example. I have the integration of dx over 5 minus 2x. This one is the improper integral. The problem on here, this time the problem not on the upper boundary, but on the lower boundary, on minus infinity. But same method, same technique. I will replace minus infinity by any number t, and I will evaluate the integration from t to 2, 1 over 5 minus 2x dx. And then I will take the limit when t goes to minus infinity. So first we need to evaluate the integration. So take u is equal to 5 minus 2x. Then du is minus 2 dx, which is minus 1 over 2. Du is equal to dx. Now this integration, I will rewrite it again in terms of u. Dx will replace by minus 1 over 2 du here. Dx will replace by minus 1 over 2 du. 1 over u. 1 over u. The integration of 1 over u is the natural logarithm of u. It's the natural logarithm of u. Write your integration in terms of x. So minus 1 over 2 natural logarithm 5 minus 2x. 5 minus 2x. Now this term, the evaluation of integration, I will evaluate it from t to 2. So this limit for this integration will equal to limit when t goes to minus infinity. The evaluation for this integration is this value. Minus 1 over 2 natural logarithm 5 minus 2x. From t until 2. From t until 2. First substitute 2, then minus substitution of t. When I substitute 2 here, 5 minus 2 multiplied by 2, which is 4. 5 minus 4 is 1. So logarithm 1. Minus substitution of t. Minus 1 over 2 here is a constant outside. So I substitute 2, which is logarithm 1. Minus substitution of t, which is logarithm 5 minus 2t. 5 minus 2t. Now this is a constant limit when t goes to minus infinity. Logarithm 1 is 0. Logarithm 1 is 0. Logarithm 5 minus 2t. This is the minus here. I can bring it here because this is a logarithm. So it become logarithm 1 over 5 minus 2t. 1 over 5 minus 2t. The limit of 0 is 0. Now I need to calculate the limit for 1 over 5 minus 2t. So I have here infinity. So 1 over infinity, any number over infinity is 0. 1 over infinity. Any number over infinity is 0. So 0 plus logarithm of 0. This is 0. Now the logarithm of 0 goes to minus infinity. This is the function of ln x. This is the function of ln x. So if you see here, ln x near 0 goes to minus infinity. Goes near 0, it goes to minus infinity. So 0 minus infinity is minus infinity. So the limit goes to minus infinity, which means this integral is diverge. If the limit equal to number, then the integral is converge. But here in this example, the limit equal to minus infinity, which means the integral, the improper integral is diverge, not converge. Okay, another example. I have the problem on the two boundaries, from minus infinity to infinity. From minus infinity to infinity. So here I have to separate the integration first to two integration. I have to separate into two integration. First integration from minus infinity to 0. And second integration from 0 to infinity. Here you can choose any number, not necessarily 0. But the easiest one is 0. The easiest one is 0. So usually we use 0. Usually we use 0. But you can choose from minus 1 to 1 or 2 or any number. But usually we separate at 0. Separate at 0. So from minus infinity to 0 plus from 0 to infinity. Now this is an improper integral. Have a problem on the lower boundary. This one is an improper integral. Have a problem to the upper boundary. So this one will take the limit. I will replace minus infinity by t and take the limit when t goes to minus infinity. For this one, I have the problem here in the upper boundary, so I will replace the upper boundary by a number s. So I will take s goes to infinity. S goes to infinity for the same integration. Okay, now I need to evaluate the integration. What is the integration of x over 1 plus x squared? So here using substitution, if you use u is equal to 1 plus x squared, then du will be 2x dx. Du will be 2x dx. So 1 over 2 du is x dx. 1 over 2 du is x dx. So I will rewrite my integration in terms of u. I will rewrite my integration in terms of u. So x dx here will replace by 1 over 2 du. And 1 over 1 plus x squared is 1 over u. 1 over u. So 1 over 2 is a constant. The integration of 1 over u is the natural logarithm of u. Natural logarithm of u. So this integration is equal to 1 over 2 natural logarithm. Write your integration in terms of x. So natural logarithm of u, which means natural logarithm of 1 plus x squared. Write your result in terms of x. So 1 over 2 natural logarithm of u, which is 1 plus x squared. So this is the evaluation for your integration. Now you have to substitute from t to 0 here and from 0 to s here. And take the limit. So first limit when t goes to minus infinity for this value from t to 0, plus limit when s goes to infinity for the same value but from 0 to s. From 0 to s. Okay, now substitute. Before taking the limit, we need to substitute. I will substitute by 0 first, minus substitution of t. Substitution by of 0, 1 over 2 natural logarithm, 1 plus 0 is 1, natural logarithm of 1, minus substitution of t, which is 1 over 2 natural logarithm 1 plus t square. 1 plus t square. Plus, now this term, I will substitute s first and then 0. Limit when s goes to infinity. Okay, so this is the first limit. And now this is the second limit. Substitute s. 1 over 2 ln 1 plus s square. 1 plus s square. Minus 1 over 2 substitution of 0, which is ln 1. Ln 1. Okay, now we need to evaluate the limit. First term is 0. Second term, this one have minus. Bring it here. So we have 1 over 2 ln 1 plus t square to the power minus 1, which is mean 1 over 1 plus t square, because we have minus here. We have minus here, so this minus will become here. Plus limit 1 over 2 ln 1 plus s square minus 0. Minus 0. Now this is a 0 is a constant. Substitute minus infinity here, so you have ln 1 over infinity. 1 over infinity. Plus substitute the infinity here, 1 over logarithm infinity minus 0. 1 okay, infinity minus 0. This is 1 should be in here. We have to substitute. We have to substitute. So this term 1 over infinity is 0. So we have natural logarithm of 0. This one we have natural logarithm of infinity minus 0. So we have this one goes to minus infinity, this one goes to infinity, which means that your answer for the limit is infinity, which means that your integral is diverge. Your integral is a diverge integral. Why? Because the limit goes to infinity. The limit is not equal to any number. So which means that your integral is a diverge integral. Okay, now this is the first type of integration when we have a boundary goes to infinity. Sometimes we have some kinds of integration. The boundaries not goes to infinity, the boundaries is numbers, but the function itself is not defined about this number or any number in between. For example, sometimes f of x is not defined at p. So we have to take the limit when t goes to b from the left, from integration a to t f of x dx. Or sometimes the integration is undefined, the function is undefined at a. It's undefined at a. So also you will replace a by a variable t and take the limit when t goes to a from right. The positive here, which means from right. F of x dx. If the function is undefined in the point between a and b, then you have to separate the integral at this point. So you have to take the integral from a to c plus from c to b. And as type 1, if the limit is a number, then the improper integral is converged. If the limit is goes to infinity, then the improper integral is divergent. Let us go for some example. For example, this one, I have integration from 0 to 1 x over 1 minus x squared dx. This integration, I have the boundary 0 to 1, no infinity boundary here, no infinity boundary, but this one is still improper integrals. Why? Because this function is undefined at 1. At 1, the denominator here will become 0. At 1, the denominator here will become 0. So this function is undefined at 1. So I have problem at the 1. So I have to take the limit. I will replace 1 by t, and I will take the limit when t goes to 1 from the left. And I evaluate the integral. This integral can be evaluated using substitution method. Take u is equal to 1 minus x squared. Take the derivative for both sides, then du is minus 2x dx. So x dx is 1 minus 1 over 2 du is equal to x dx. Now we need to calculate the integral, this one. So x dx will be replaced by minus 1 over 2 du. 1 over square root 1 minus x squared is u. 1 over square root of u. This one is u to the power minus 1 over 2. So the integration as a power function, plus 1, which is minus 1 over 2 plus 1, 1 over 2, divided by 1 over 2, and here we have minus 1 over 2 as a constant. So 1 over 2 will cancel with 1 over 2. So we have minus u to the power 1 over 2, which is square root of u. In terms of x, it is equal to minus square root 1 minus x squared. So this is the evaluation for integral. Go and we evaluate substitute from 0 to t and calculate the limits. So this one will be the limit when t goes to the 1 from the left, minus square root minus 1 minus x squared from 0 to t. Substitute t first. So we have limit. So we substitute by t first, then 1 minus t squared, limit minus limit when t goes to 1 from the left. I will substitute t first, so 1 minus t squared, minus substitution of 0. The minus this one become outside of the limitation. So substitute t and then substitute 0. So minus substitution of 0, 1 minus 0 is 1, square root of 1 is 1. So minus 1. Now the limit when t goes to 1 from the left, 1 minus t squared, substitute t by 1. 1 minus 1 is 0, square root of 0 is 0, minus 1. Minus 1, minus 1, which is 1. So the limit is 1, which means this one is converge. This one is a converge integral. Okay, another example here. We need to determine if this improper integral is converge or diverge. Here we have a problem at the 1, because 1 minus x squared will be equal to 0 at 1. So the denominator will be 0 at 1. So we have the function here is undefined when x is equal to 1. So we have an improper integral at the lower boundary here. So I will replace the lower boundary 1 by variable t, and I will take the limit when t goes to 1 from the right. So the integration will become from t until 2 dx over 1 minus x squared. Because this one integration, I will evaluate it by using partial fraction, because 1 minus x squared can be written as a multiplication of 1 minus x and 1 plus x. Linear factors, so the top are constant. So we need to know the values of a and b. I will take the 1 here equal to a multiplied 1 minus 1 plus x plus b multiplied by 1 minus x. To find the value of a and b, take x equal to 1. When x equal to 1, this term goes to 0. So you have 1 is equal to 2a. 1 plus 1 is 2a. Which means that a is 1 over 2. X minus 1. 1 minus 1 is 0. 1 minus 1 is 0. So this term goes to 0. So 1 minus minus 1, which is 2. 1 is equal to 2b. So b is equal to 1 over 2. So the values of b is 1 over 2. The values of a is 1 over 2. So I will replace a here by 1 over 2. So this 1 over 1 minus x squared is equal to a is 1 over 2, which is 1 over 2 integration 1 minus x dx. A here is 1 over 2 is goes out as the constant outside of the integration, plus integration of 1 over 1 plus x, and b is 1 over 2 constant outside dx. So I will evaluate this integration and this integration. This integration is equal to 1 over 1 to 1 over 2 logarithm so logarithm 1 minus x multiplied by minus, because here we have minus x, so minus 1 over 2 logarithm 1 minus x, plus 1 over 2, the integration of 1 over 1 plus x is the logarithm 1 plus x, so this integration logarithm 1 minus x multiplied by minus, because we have minus x here, and here logarithm 1 plus x. So this is your integration. So I will substitute from t until 2, and then I will take the limit. When t goes to 1. So substitute from t until 2 for this value. First I will substitute by 2 minus substitution of t. When I substitute by 2, logarithm 1, absolute value of minus 1, which is 1, so goes to 0. Now 1 plus 2 is 3. 1 over 2 logarithm 3 minus substitution of t. Minus minus become positive. 1 over 2 logarithm 1 minus t minus 1 over 2 logarithm 1 plus t. So when t goes to 1, this value is 0. This value is 1 over 2 logarithm 3 here. So I will take the limit when t goes to 1 for these two values, for these two terms. 1 over 2 logarithm 1 minus t minus 1 over 2 logarithm 1 plus t. Now this is a constant. Substitute 1 here. So 1 over 2 logarithm 1 minus 1 is 0. Here substitute 1 plus 1 is 2. So this is a number, the problem only in here, logarithm 0. Logarithm 0 goes to minus infinity. Goes to minus infinity. So all the term here goes to minus infinity. Which means that the limit does not exist. The limit is diverge. Limit goes to infinity. So the limit is diverge. This is the last example that we have in this chapter. We need to find the integration of logarithm dx from minus 1 to 1 logarithm x dx if possible. Here it cannot possible integrate the integration because we have from minus 1 to 1, and logarithm is a positive function. The domain of ln x, the domain of the function ln x, the domain of the function ln x is from 0 to infinity. So from minus 1 to 0 the function is undefined. So this one not possible. Okay, so to evaluate this one, we can replace the question. We can evaluate from 0 to 1. Logarithm x dx. This one is improper integral because the function only is undefined at 0. So here the domain is not from 0 to infinity. Sorry, this one from 0 is not included. So we can calculate this one as an improper integral. So it will be equal to the limit. So this one will become the limit when here only the undefined for the function only at 0. So we will take t goes to the 0 from the right, t to 1 ln x dx. Now how we need to evaluate the integration of ln x. So I will use by integration by parts. I will take u is equal to ln x, dv is equal to dx. I will take the derivative of u, which is du is equal to 1 over x dx, and the integration here v is equal to x. So the integration from ln x dx is equal vu, which is x ln x, minus integration v du, which is x multiplied by 1 over x is 1, so dx. So this one will become x ln x minus x. This is the evaluation for integration. Now I have to calculate this one from t to 1, So limit when t goes to 0 from right, okay, the integration from t to 1 ln x dx will equal to limit when t goes to 0 from right. Now the integral of ln x is x ln x minus x from t to 1, First I will substitute 1. So 1 logarithm 1 is 0 minus 1. So I will have limit when t goes to 0 from right, 2, 0 minus 1. Minus substitution of t, so minus t ln t plus t when t goes to 0. Now you have to substitute 0, so you have 0 minus 1. So here this is minus limit t to 0, t ln t. When I substitute by 0, so this one is 0. So now the problem is here. When I direct substitute, will become 0 logarithm 0. 0 logarithm 0, which means 0 minus multiplied by infinity, which is undefined. So this one here, I have to calculate now this term, this one. So limit, this one 0 minus infinity, which means you have to apply Hopital rule. Why? Because when t goes to 0, t ln t. This one same is equal to limit when t goes to 0 logarithm t over 1 over t. T here is equal to 1 over t. So ln t 1 over t. T here can be written 1 over t. Now direct substitution, logarithm 0 ln 0, which is infinity. 1 over 0 is infinity also, so infinity over infinity, I have to apply Hopital rule. Hopital rule, I have to differentiate the first one and the below one. So it will become equal to limit when t goes to 0. Now ln t is 1 over t over 1 over t. The derivative of 1 over t is 1 over t square. 1 over t square minus 1 over t square. And this one is equal to the limit when t is go to 0. Okay, minus t square over t. T square over t, which is equal to limit when t goes to 0, t square, because t square here will go above and t will come below. This one will go above, t will come below. So t square over 2, which is minus t, which is 0, which is 0, which is 0. So here when you go here again, so 0 for this function, so we have this function will be equal to minus 1. Why? Because this limit is 0. This limit is 0. This limit is 0. So 0, all 0, this one only minus 1. So it is a converge. It is a converge. It is a converge. 1. So our integration is converge. Why? Because this limit is equal to 0. It's equal to 0. It's actually infinity over infinity. Applying Hospital rules become 0. This is by this example we end chapter 5.